In the last 3 videos, if we want to denote a sequence of symmetries done, we would draw a little flow chart. But this is a little space consuming, so we would abbreviate as tau, zeta, sigma. It might be a bit strange that we read off the sequence of symmetries from right to left, but when we think about how the symmetries act on X, it makes sense to abbreviate this sequence this way. If we first let sigma act on X, we get sigma star X. Then we let zeta act on this result, so it is now zeta star sigma star X. And finally, we have tau to act on this result. Now we have the symmetries in the exact same order in the abbreviation. Another abbreviation we would make is about undoing symmetries. Previously, we just say undo sigma for a symmetry that undoes sigma, but we can abbreviate this to be sigma to the power -1. We usually read this sigma inverse. Looking at these two notations, it seems like we are multiplying symmetries, but please don't treat it like normal multiplication. To illustrate this, consider the symmetries of a regular hexagon, and denote R to be the symmetry that does an anti-clockwise rotation by 60 degrees, S to be a reflection along the horizontal axis. On the left, we will do the symmetry S first, then R. And on the right, we will do the symmetry R, then S. We now place a red dot for tracking what these symmetries do. On the left, we do a reflection first, then a rotation, and the red dot is up there. On the right, we do the rotation first before reflection, and the red dot is down there. So these two are different, so please don't treat this abbreviation as just normal multiplication. So now we can talk about conjugation with more succinct notation. Conjugation looks something like this. You put the symmetry H you want to conjugate in the middle, and you sandwich H with G and G inverse, where G is the symmetry you conjugate H by. The reason why I emphasize that this is not normal multiplication is that H after conjugation is not the same as H itself. In fact, GHG inverse and H are very similar to each other, though not necessarily equal to each other. But how similar are these two symmetries? We will again use the example of the two symmetries of hexagon, and we consider the conjugation of the horizontal reflection by an anti-clockwise rotation. We first do a symmetry that undoes R. This means a clockwise rotation of 60 degrees. Instead of actually doing a clockwise rotation, we do something different this time. Imagine this is you, and you are facing to the left. Now notice that the horizontal is the direction you are facing. So now, to do this clockwise rotation, we would shift our perspective instead. Rotating our perspective anti-clockwise while holding the hexagon still is the same as a clockwise rotation. So now we need to do a horizontal reflection. Remember that the horizontal in your perspective is the direction you are facing. So this green dashed line is the horizontal. S here means the horizontal reflection along this green line. So now we need to do an anti-clockwise rotation, which is again the same as shifting the perspective. This time we shift the perspective back to what we started off with. Now notice that what we have done is reflecting along the screen axis. So before conjugation, S itself is a reflection along the horizontal axis, but after conjugation, it becomes a reflection along the green axis. So S being conjugated is still S, just viewed in a different perspective. And here, S is conjugated by R, and R determines how you will change your perspective. So now we can answer the question of how similar these two are. These are actually the same symmetries, but viewed in different perspectives. I repeated myself twice because this is a really important intuition to have for conjugation. To make sure we get the intuition right, we revisit the hexagonal symmetries. This time, we will conjugate R by S instead. According to our intuition, this is basically just another anti-clockwise rotation in a horizontally reflected perspective. In a normal perspective, this red dot will rotate anti-clockwise with the hexagon. But now, in a reflection along this horizontal axis, the rotation becomes clockwise. This means that this conjugation results in the inverse of R, because it is a clockwise rotation rather than an anti-clockwise run. And this sort of relationship between these symmetries is now easily unveiled, while previously you might need to see where these symmetries send each vertex to. Conjugation gives rise to many other important concepts in group theory, and for the rest of this video, we will focus on normal subgroups and simple groups, and leave the quotient group concept for now because I will cover it in the next video. But for the normal subgroup, we first need to revisit the concept of a subgroup mentioned in just the previous video. This was what we came up with when we discussed Lagrange's theorem in the last video. To make the concept of a subgroup and ultimately normal subgroups more concrete, here is a non-trivial example. We will consider a subset of symmetries of cubes. Of course, the identity has to be there, it is in one of these properties. Then another symmetry in this subgroup is rotating by 90 degrees. We also have rotation by 180 degrees as well as by 270 degrees. To show that this set of symmetries really is a subgroup, we first check that composing any two symmetries in a set gives you some symmetries inside the set. This is not difficult to check because if we first do a rotation by 90 degrees, then do a 180 degree rotation, this is the same as a 270 degree rotation. In fact, you just add up the angles and subtract 360 degrees from it if necessary. And the identity is visibly in the set of symmetries here. So now it comes to undoing symmetries. Undoing the identity is of course still the identity because we have done nothing in the identity symmetry. This case is the same for a 180 degree rotation. The way to undo a 180 degree rotation is to do it again. And the remaining two undo each other. A 90 degree rotation undoes the 270 degree rotation and vice versa. And so, this set of symmetries really is a subgroup. Previously, when we think about conjugation, we only consider conjugating a symmetry by another symmetry. But what about conjugating an entire subgroup by G? It simply means that we conjugate each symmetry in the subgroup by the same symmetry G. The collection of these conjugated symmetries will be denoted as GHG inverse. Like conjugation of a symmetry, this resulting set of symmetries should be very similar to H itself. And in fact, this set of symmetries form a subgroup itself because these properties hold as long as you view the symmetries in the same perspective. But these two subgroups are not always equal. For example, when we look at a subgroup of symmetries of a cube we just discussed, these symmetries are rotations about a vertical axis. But when you look at the symmetries from above, these will become rotations about an axis pointing into or out of the screen. These two subgroups are definitely different because the axes of rotation are already different. So if we call this subgroup H, then this subgroup on the right is GHG inverse for some symmetry G, and they are demonstrably different. However, although in general they are not equal to each other, in some cases they do equal to each other. What I mean by them being equal is that for all little h inside the subgroup H, conjugating it by G gives something in the subgroup H. We are not saying it has to be H itself, just somewhere in the subgroup H will be fine. In this special case, the symmetry G is said to be normalizing H. And in the exceptional case where everything normalizes the subgroup H, or in other words, the subgroup H looks the same in every possible perspective, we say H is a normal subgroup. There are always two normal subgroups, namely the set only including the identity as well as the whole group of symmetries itself. The reason for this set to be normal is that the identity viewed in whatever perspectives is the same, doing nothing. And for the whole group being normal itself is because conjugating any symmetry by any symmetry is still a symmetry, so it is still inside the group G. Lastly, if there are no more normal subgroups of G, then we say G is simple. It might be a bit tricky to remember the definitions of these new terms, normal subgroups and simple groups, but the simpler takeaway is that normal subgroups look the same under all possible perspectives, and simple groups are simply those with a minimal number of normal subgroups. The reason why we are so interested in these concepts is to allow the definition of a quotient group, and we will see in the next video why this is a very useful concept. If you enjoyed this video, give it a thumbs up and share it. Don't forget to subscribe with notifications on to know when I put up a new video in the series. See you next time!